Sir, I think we can get started.
If we are expecting anyone,
yeah, actually 3 more folks, I think 2 at least, they were joining regularly. I don't know why they have not joined.
is there a way to give them some information? The only point is that this initial 10 to 15 or half an hour is actually crucial.
Yeah.
But anyways, yeah, we are going to record so they can revise if they want.
Yeah.
If that is okay.
Let me message once. 1 second.
Okay, you message it once. If they come, then it's okay.
Yeah. So by 8:15 we can get started.
Okay.
Sir, I think we can get started. They might be late in joining because I have messaged them.
Okay, fine. So let me. So what we are going to do today is that we are going to talk about first that remaining part of our recurrent neural networks. In recurrent neural network, whatever we have seen till now was the vanilla neural network, or one can say the basic recurrent neural network. After that, what we have decided is that there are some problems with that, and we have designed another neural network that is again a recurrent set of neural network, but having slightly better performance than RNN. In fact, much better performance than RNN. That is actually GRU, that is the gated recurrent unit. And using that gated recurrent unit, if you slightly vary it, then you can move on to that's something which is called as LSTM. That's a long-term short-term memory. So these are the three models that we are going to cover, and that's also going to be used in our lab in our upcoming time. So very soon we will review the previous thing and finish GRU as well as LSTM. With very minimalistic changes in GRU, we can realize LSTM, and the performance of LSTM is actually even better than GRU in several cases. So before going to start about this, some amount of recap. So the recap is that yes. So our recap is that in recurrent neural network, whatever we have seen, suppose that this is my recurrent unit that I'm trying to somehow design. So it is going to take some input, that is going to be some xt, some input at some time t, and it has to produce yt at that point of time. But it's not that it's directly going to produce this yt. There is some history, we have some memory, we have some scratch pad, we have some amount of variables, some 128 dimensional history. Somebody can have 128 dimensional history, so it's going to be something like a 128 dimensional vector. And that vector, so along with this input, I am going to use my previous history, and the current input is going into a neural network, that is N1 neural network. Previous history is going into another neural network, that is N2 neural network. I add both of them, apply some activation function, and I am going to get the AT. That is going to be my current history. That is my previous history. This is my current history. This is my input. Once you have got the current history, it is going into a third neural network, and uh, that third neural network, and this third neural network is going to produce the output at that point of time. The current the out in for the current input xt, we are going to get our yt. That's my output. So here you can see that I'm having three neural networks. If I say I am having three neural networks, it's essentially like I am having a set of weight vectors. So if I say that for this neural network I am having set of weights something like w3, suppose that's a w3, and the bias is 3, and then I am having weight 1 and the bias 1. So these are actually weight vectors. These are fully connected networks. I'm giving just the weights for them. And what we have shown in my previous lectures is that how can we somehow concatenate two things. What are those two things? This as well as this, one in horizontal direction, other one is vertical direction. Whatever concatenation that we have done, it's essentially bunch of weight vectors, and it's been designed it in such a way so that instead of showing this and this as two things, if I show them as one neural network, then xt and the previous vector, previous history, and the xt, both of them are directly going in my network as an input. So it was like that. Merging suppose that merging w1 and w2 in the way as I have said. Suppose that I used to get say w12, then this is my weight vector, say w12. It is going to take input as xt and at minus 1 concatenated in this way, and I am going to get the output that is going to be at. And this AT is actually going into another neural network that we used to say as W3 neural network, and you are going to get the YT. So this was the thing that we have seen, and what we have analyzed is that is the way in which, if you wanted to do some previous history, use the previous history, how can we use that? And and the problem that we have seen is that these type of network that are going to have is that xt is actually being dependent. So we can see that the xt is actually being dependent upon the previous things as well, and this at minus 1 is actually being dependent upon at minus 2. At minus 2 is actually dependent upon at minus 3, which is dependent upon at minus 4. So this whole thing is actually being dependent upon so many things which are being in the previous things, and you're in a single RNN unit is actually being unfolded in so many things, and because of that, this weight, this thing somehow have to be back propagated here, then there, and so on, and so many back propagations are actually having, and we have shown that thing maybe over here. And because of that, what happened is that as you keep on back propagating as back as possible, uh, these repeated multiplications are going to happen. Repeated multiplications will end up, if the value is more than 1, then they blow up. If the value is less than 1, then they vanish. In case of recurrent neural networks, gradients most of the time got vanish, and if they vanish, then what will happen, that this YT will only be dependent upon not too many things which are far back in time, that the network has seen far back in time, but it's essentially being dependent upon the things which it has seen very recently, because of the fact that the things which are very far in time, these things are not going to play huge amount of role, because the gradient got vanished. Only the effect of the previous things which are very near in time, they are going to somehow affect how my YT is going to be generated. This was the problem, and to come up with a solution, we have talked about certain things, and that is the thing that I'm going to talk about. That's a GRU. In the case of GRU, what we have said is that AT, all we understand is that our history, this is the history that we are going to use, and we are going to use this history, that's the history at time t. There is a candidate history which is supposedly, that I want to change this AT. This is actually the scratch pad, if I say, that you have in your copy, and you one page in which you are going to write whatever the things that you feel that are important and can be useful whenever next you are going to revise this thing. So everything should have to be over here, and given xt and AT minus 1, you are going to predict the next AT. This was the thing that's been done in our basic CNN. Here I am saying that I am updating this. So in order to update AT, I am updating it, having a candidate update, candidate history. I'm saying that this is going to be my candidate history. Whether this is going in this or not, that is the thing that is somehow we are going to understand. But in the case of GRU, I am saying that we are going to have certain gates. So first thing is that in the case of GRU, the history, and suppose that this is my raw history or the rough history. It is actually like that you have got a page over which you are writing. Whatever you write, you assume that that is your final answer, and you keep that thing. So that is actually GRU. In the case of LSTM, he is actually a better guy. He used to say that whatever I have written in that piece of paper, that is my rough history. Before going to submit it and saying or declaring that this is going to be my final history, this LSTM actually does one more time refinement of this CT. This is just like that. First you write during my class, and before going to declare that that is going to be your final history, you update it once more. You just find out, okay, these are the important things. You color it, you underline it, you remove certain thing, you add certain thing. So whatever you wanted to do, you wanted to do over CT. So LSTM, when we talk about this LSTM, one of the change is that GRU say that my final history is actually just the same as my rough history. LSDEM says that my rough history, I just wanted to somehow update using another network or a gate, and then I am going to get my final history or the final content vector that we are talking about. The other things that in GRU what we have seen is that we wanted to somehow know that I wanted to update. So where to update? So we need to understand what to update. So what to update is one thing that we wanted to somehow understand, and where to update or when to update. So if I know that this is the candidate history and we are saying that we wanted to update it in this way, update gate is going to tell that what are the places where I wanted to update. I wanted to update over here, I wanted to update over here, I wanted to update over here. Only these places are going to be updated. So no matter what are the things which are written else on else other places, only these this and these places are going to be updated. That is the role of my update gate, and this update gate is somehow going to be learned via neural network. One more thing was that the relevance gate in the case of GRU. So GRU says that not each and every candidate history is important. There are certain things which are important, there are certain things which are not very important. So I wanted to learn another gate. Gate is again a neural network which is going to somehow learn that what are the places, how relevant this information is, how relevant this information is, how relevant this information is, and all this in these things which are how much amount of information or how much amount of relevance is actually being there. It is going to be learned. Once we learn, there is one more thing which was being there. So that is why I've said that tau u, that was actually the update gate. When to update, 1 minus tau u is saying that when not to update. This is the second point. Here, if I say that I have got a vector, I have got a b vector, and then suppose that ci is equal to ai multiplied by bi. So it is just that I take this thing and this thing, I multiplied this and place it over here, this and place it over here. So if it is say 10 dimensional, this is also 10 dimensional, you are going to get a 10 dimensional vector in which ai got multiplied by bi and you are going to get a ci. That is actually point by point multiplication. Now if I say that few places I am having 1 and remaining places I am having 0, so now you can see that only these places you are going to have ai bi, here you are going to have a 0. So what happened is that these are actually shutdown gates. These are not allowing a to be coming out over here, and here you are not having ai bi, actually you are having directly a1. Here you are having 0, here you may be having 0, and here you may be having maybe a4. So a is being updating and it's updating this c, but it is not allowed to update each and every position. Only update gate is going to tell you that what are the places where you can update. So that is why this is my update gate, this is my update gate, and this vector is trying to update, and when I multiply, this is going to be my final update. With this, let us go and dive into whatever the place where we were in our last lecture. So first thing was that I wanted to update. How can I, and one more thing that I need to tell over here, that gate is nothing but a neural network, and it's going to be learned, and there has to be, suppose that it is some tau u gate, suppose that's a tau u gate, then I need to get some weight vectors, some tau u weight vectors and the corresponding biases weight vector. So if I know these things, I am done. So whenever I say that I wanted to learn a vector by which I understand that what is the relevance of each and every historical vectors bit or the byte, which essentially mean, or the location, which essentially mean that I wanted to learn those things via neural network. So neural network is going to take something as an input and it is going to give me an output which is going to be a vector like this. If I want to learn that what are the places where I wanted to update, so neural network is going to take certain things in and it is going to have to give me something out which is going to be something like this, and then I use this output vector or whatever the output vector of my gate and multiply in the way I have intended to. If it's a relevance gate, it is directly multiplied. If it's so here if I say, so here if I say that that is my relevance gate, so it is saying that I suppose that this CT is actually a 10-dimensional vector, then this thing is also a 10-dimensional vector in which each and every location or the every value in this 10-dimensional vector is going to tell the importance of that particular location in the CT. How much amount of importance one should be giving to fifth location is going to be set by this fifth position of this relevance vector. Similarly, if I have some candidate update, I wanted to update my CT by this, it is saying that you can, but you cannot update in whatever way that you want. You wanted to update is okay, fine, but you will have to find out that what is the places where you wanted to update. This is going to be somehow learned by another neural network. So given these updates, only these places are going to be updated. What are the places which are not going to be updated? These are the places which are not going to be updated, 1 minus that. So these places are not going to be updated. One can say that we are not remembering them. So if so these places, if they are not being updated, we are not updating. So what has to be there? It has to have the previous value. This is the current value that we are going to update, and the remaining places we need to have the CT minus 1. With these two things, very easily now we can understand the whole stuff of RNN and then its transition from RNN to LSTM. As I have said that this was the weight vector and this is actually the inputs. So I wanted to update. So let us directly go to maybe I guess the simplified.
Adit sir, I have one question.
Yeah.
As you explained the rough, go to previous screen, sir. Yeah. So rough history and history, two difference you told. What is the meaning for that? Can you give me a real time 1 or 2 scenarios so that we correlate with that?
Yes. See, real history and the rough history are actually, so that's what I have written. First of all, this is my rough history and this is the real history. First of all, let us make it very clear that in the case of GRU, rough history, in the case of GRU, you can see that the rough history and the real history, they both are same in the case of GRU.
So my question is that, I mean, I'm not correlating with the real and rough history. Means history is a history, right? And then what is the difference between rough and real history?
Yes. So first make it sure that we are having two different type of history or the context. History and context is actually I'm using very loosely that history or the context that you have seen till now. In the case of GRU, both of them are same. I'm going to talk about that. Wait for a minute. I am saying that for GRU they are same. For LSTM they are different. I will talk about them. But now let us think about two students who are taking my course. One student is actually GRU type of student who write whatever he is writing in his sheet. He is assuming that that is final. He is not going to read it again. And if I ask in my next class, if I ask anything, he is going to use the same piece of paper, because that is his final history. Okay. Instead of that, LSTM is a guy who will say that, I have got something that is my rough history. Before going into the class, I will underline, I will mark, I will rewrite, I will get certain more things out of that. So I apply a function over my previous history, or one can say the rough history, and then get the final history. That is the difference.
Okay, got it. One history is that repeating that same activity, and another is variation will be there. Correct?
Yes, that's a variation is there. Yes. Yes. So that is why LSTM is slightly advanced than GRU.
Great, sir. Yeah.
Fine. So let us go and one by one see this very easily. I assume that now we can understand the first of all the full GRU. The full GRU, we have to just understand that that CT. So I did not to do this. Yeah, this CT, what I am saying, let me take this red it over here. This CT, this is my previous, cell value or the history that I am saying. So previous this thing, every every cell is not having useful information. I am saying that I wanted to learn, weights for each and every information that I have in my previous cell or the history, the previous history. That is why I learn this thing. How to learn? I have applied again a neural network. So if I show you a long expression like this, in which I am having a weight vector, in which I am having a input, and in which I am having a bias, then this is essentially nothing but a neural network. So I am learning this thing via neural network, and then when I do this, this is actually the relevant bit or the relevant information that I have in my context. So this is my relevant context that I have got till now, and that is going to be my input. Instead of directly taking this CT, I am taking the relevant CT minus 1 multiplied by my relevance. You are going to get a relevance, previous history, and along with that I am having the current input, and both of these things are going into this WC. I am going to get an output. I apply a bias over that, and then apply this function over that, sigmoid tan h function over that, and that is my candidate history. I feel what I have learned over here is that this has to be some, so CT, if you want to convert this C2 into the next time step CT, it has to be updated in this way. This is my single neural network that I need to learn. What are the things that you need to learn? You need to learn this value, you need to learn this value, and also you need to learn this. How you are going to learn this? There is a separate neural network over here in which the same things are going to be input, and it is going to output me that what is the relevance of each and every bit which is being there in my CT minus 1. Once I learn these things, once I learn this, I have got the update that I got, but you are not allowed to update with this. You need to learn another vector. This is going to tell that what are the places where you are going to update, and the remaining places are not going to be updated. So I have got another neural network in which the weight vectors are WU and BU. Same input. Here it was actually that relevant input which is going. Here it's a direct input which is going, and you have got a neural network which is taking the input as a previous history as well as the XT, and in the case, and that is what I am saying, that in the case of GRU, the rough and the actual history remains to be the same. That is why you can say that is the rough history or the previous history or the current context. Everything remains to be the same in the case of GRU only. So you have got a neural network which is somehow have learned that given these two things, it has learned that what are the places where I wanted to update, and 1 minus of that, the places where I do not wanted to update. So final CT is going to be the places where you wanted to update and what you wanted to update. Places where you wanted to update and what you wanted to be updated. This is actually the point-wise some multiplication that I just have previously told you. 1 minus of that, we do not want it to update. So 1 minus of that is going to be multiplied with my previous history. That's a CT minus 1. I'm only going to change these places by this, and the remaining places remains to be the previous history. So now you see that that's my final candidate update. This and here, that's what I've said, that the AT and CT, they are same, because that's my final history, and final history is actually the previous the raw or the rough history that I just have got. Till now, that was a GRU, full GRU for you, and along with this full GRU, what we are going to do is that GRU to LSTM, there are 2 or 3 only things which are being changed, and we are done. So let us see. In the case of GRU, we are having a relevance gate. So in yellow color, we are having GRU. In green color, we are having LSTM. So and the left side is actually GRU, and the right side, towards this right side, is actually LSTM. First I write GRU, then I will write LSTM. Now let us see. So in the case of GRU, what we have said is that there is a relevance gate. In the case of LSTM, it says that no, I do not want LSTM. LSTM says I do not want any relevance gate. So now you can see that is my candidate update for GRU. This is a same candidate update, same functions, but here you are not having the relevance gate. This is the first difference. The second difference is that in the case of GRU, you was having a update gate, which is going to tell you that what are the places where you wanted to update. Okay. In the case of LSTM, we are also having an update gate, exactly the same. In GRU, we are having this update gate. In LSTM, we are having the same type of update gate. Now you remember that in the case of GRU, tau u is the update gate, and 1 minus tau u is the gate by which you do not want it to update. In the case of LSTM, I am having one gate to update, in which I am saying that what are the things that I wanted to update. 1 minus of that can be used as places where not to update. But GRU uses that. LSTM says that instead of that, I am learning another gate, and it says that tau u I wanted to update and tau f I wanted to forget. Instead of 1 minus tau u, which I assume that what to forget, I am saying that instead of that, I wanted to learn tau u, another neural network that is going to tell me that what to update and what to forget. So what to update is going to be things over here, and what to forget, which was actually being missing in the case of GRU, and we use 1 minus tau u for that. Here we are going to learn another gate, that is the places where you want to forget, how much you want to forget. So now you see that that was actually in the GRU we are having a relevance gate, and in the case of LSTM, instead of this relevance gate, we do not have this relevance gate, but we are having a forget gate, which is again going to take the same things. But along with this forget gate, we have got a new type of output. A new type of uh, update that we are going to get. In the case of GRU, what was the update? Tau u CT 1 minus tau u CT minus 1. But in the case of LSTM, tau u CT, but tau f CT minus 1. Just see the difference. That is actually this I wanted to update, this I do not wanted to update, this I wanted to update, and I learned another thing, tau f, the places where I do not want to update. And that is the difference between this, that 1 minus this. So here we are having only one gate which is acting as what to update, what not to update. Here what to update one gate, what not to update is another gate. So because of that, you have got much more non-linearity, much more functional stability. Because of that, you can learn explicitly what to update, what not to update. If you want to update the things, then this is the candidate update that you wanted to update. Each and every place you cannot update, so you only update these places. Here you wanted to forget, what are the places you wanted to forget, which essentially mean that I am not updating. So here you want to say that out of this, what are the places that I am not interested, I wanted to somehow forget. So if you want to forget, those places are not going to be there, only how much amount of remembrance that you wanted to have. In the case of GRU, and one final thing which is being left, in the case of GRU, AT and CT, both of them were same, as I just have said that the previous rough history and the final history. Here in the case of LSTM, we are having another gate which is actually called as my output gate. Another gate which is actually my output gate, that is the LSTM, which is actually saying that I will take the output that I have got, that is my CT, final CT. But before going to convert and say that that is my final AT, I apply and send it to an output gate. This output gate is actually a gate which is actually taking something and taking CT and somehow convert it into a better version of CT. So how it is going to do that, that is the thing we just are going to see. But before that, this output gate is again a neural network which is going to be learned in such a way so that when this got multiplied with my actual CT in this way, it is somehow going to give me the final output. So in the case of GRU, CT is my actual final AT. Here your AT is final, but it's not CT, but it is actually being multiplied by this tau u. How you have got this tau u? Tau u is being applied, or means tau u is actually being somehow achieved or being learned and by another neural network, which is saying that once you have got this CT, how this CT and how much amount of importance is there in each and every place. So you can somehow manage and modify this CT once more using this tau o. Tau o is going to be multiplied by this, and you are going to get an AT as the final thing. So that is actually LSTM. Only how many differences are there? In the case of GRU, you was having a relevance gate. Here you are not having any relevance gate. In the case of GRU, you was having tau u to remember. In the case of LSTM, we are also having tau u to remember, but instead of this relevance gate, it is having a forget gate. So by tau u, you remember, by tau f, you forget in case of LSTM. And once you have got your final history, you use another neural network, that's a output gate. So how to convert CT into a proper output, proper AT, or the history that you are looking for, that is the output gate for you. So update rule is going to be, here you are having tau u and 1 minus tau u, here you have tau u and tau f. And there it was that CT is equal to AT is equal to CT. Here it is not equal to CT, just a multiplication by tau O. So this is actually the major difference between LSTM as well as LSTM and GRU. And my suggestion is that I hope that this time it's going to be slightly better than whatever your understanding was in my last lecture. And hopefully if you read it slightly more times, then you may get, better understanding, or some other questions you can again ask me. And now my point is that after this we have planned a lab session. So Daksh has to start the lab for our next this session. So is this okay, and we can start the lab?
Yes, sir, till now okay. We'll review the video also one more time, but it's okay for me right now.
If it's okay for you, then it's good. And my suggestion will be that if you have any question, then you can ask. And while asking, I mean, you can directly ask question to WhatsApp or something. So I can even answer via WhatsApp if you want. And or you can write whatever we can answer. But mostly my suggestion is that you keep on listening to this video lecture 1 or 2 times, and I hope that you will be able to get the things.
So Adit sir, always I jump to real-time example. So one, you have given the history, how we get that one. So mostly relate to that, what the scenario and how we implement. Maybe the Daksh will help us while you're doing that practical.
Yeah. So as I said, how to implement, the thing is that I don't know that which language Daksh is going to use. I assume that he is going to use TensorFlow or Keras. So there is single line, only one line that you will have to write. That is for LSTM, that is for RNN, that is for GRU. You just have to write LSTM something, 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 and it is done. You just have to write RNN something, 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 and it is done. And if you write GRU, then it is done.
Correct,
what are the parameters?
Yes. So that we understood, the formula we can use and all. But my question is that whatever the step you had explained, so we need to keep in mind where to use, when to use this formula.
Okay.
Correct?
Yes. So that is what I am saying, that suppose that you have got something in which you are very easily feel that there is not a very long-term dependence. If there is not a very long-term dependence, then we use RNNs, recurrent neural network. But I can tell you that even for, you are talking about 5 to 10 words, dependency, 5 to 8 words previous dependencies, then a recurrent neural network will not be able to perform anything. And because of that, in most of the time, every time we are going to use LSTM.
Okay.
GRU, we have just explained GRU so as to make you comfortable with LSTM. So GRU comes in between and just make a better understanding of LSTM, and ultimately we apply LSTM everywhere.
I believe so, because a lot of scenarios comes in LSTM.
Yes. So LSTM has a complete set of testing, huge amount of thing, and LSTM is not a very new thing. It was being developed at least 20 to 25 years back, and after developing LSTM, they have designed at least 50 to 60 different types of LSTMs, and then they have come up and stick to the version that just I explained it to you. That is the best possible LSTM version. GRU is also a specific type of LSTM, if I say.
Oh, okay.
So everyone stick to LSTM and say that this is the best possible model for a recurrent neural network to learn something very easily. If you come up with few more gates, you can say that instead of that, I can add few more gates. Instead of outputting via one gate, you can say that I will add 2-3 more output gates. So everyone has initially started to think about that, and they tweaked their model and do whatever they want. And then they have seen that very slight amount of variation you are going to get, very slight amount of performance gain you are going to get as compared to the basic LSTM. So if that is the case, then why not use the most simple and the best possible model, which is not too much complex. So LSTM is having good amount of complexity, but it is not that much complex than other models, and the performance is also very good. It's difficult to beat LSTM several times.
Yeah, correct, sir.
Yeah, so that is the point. So now I'm going to call Daksh, and he is going to continue with this. It might take 5 minutes or 7 minutes for him to join, because I will call and then he will join. Okay.
Sure.
Okay. Let me call him. So meanwhile, Daksh has joined and he is going to share his desktop.
Sure.
Okay, fine. So I will be leaving. Thank you. So in the next lecture, we are going to see other things.
Sure. Thank you, sir.
Okay then. Bye bye.
Thank you.
Thank you. Bye bye. See you. Leave.
Okay, hi. So everyone can hear me?
We are able to hear you.
Okay. Okay, so sir has covered RNN, right? RNN and LSDEM. And I just want to ask one thing in that. Did sir cover truncated back through time?
No.
Okay. Okay, so right. Okay, so in today's session, we will be seeing two tasks that we will be doing with RNN. Wait, let me share my screen. Yeah, okay. Yeah, my screen is being shared now. Okay, so we will be doing two tasks with RNN. So first task would be text class be test. So in text classification, what we are trying to achieve is that uh, given any type of text, we want to classify, we want to say something about that text. Like for in this example, we are given the reviews of a movie. So we have a text in which we have a movie review. So given that movie review, we need to say whether the movie review is positive or negative. So for example, let's say the review is this movie is good, so it's a positive review, and otherwise the review can also be negative. So given any movie review, we need to tell whether the review is positive or negative, and so that's the first task. That's text classification with RNN. And in second task, we will be generating new text. That's text generation. Okay, and for that we will be using the Shakespeare dataset. It's an inbuilt dataset, and so we will teach our RNN all the text of Shakespeare, and then tell the network to predict new Shakespeare's sort of like Shakespeare's text. Okay, so this is a function for plotting. So here's the dataset that I'm going to use. So the dataset that I'm using is IMDb reviews dataset. Okay. So so in the IMDb reviews dataset, okay, I have training examples and testing examples. Uh, Now to load this dataset, what I'm doing is I'm using the inbuilt TensorFlow's dataset API. So TensorFlow dataset API, there's an API of TensorFlow datasets. Now this API contains a lot of datasets, and these datasets are already pre-processed for the deep learning modules that we want to train on them. So not a lot of pre-processing is required, but despite we don't have to pre-process this data, but we will still show how the data has been pre-processed. But the data is already pre-processed, but still I will show it to you that what is the pre-processing that has been done on the data. Okay, so that one can actually understand that why do we need this pre-processing, and what is the pre-processing, so that we can actually do that on our own data sets. But when I load this dataset using the TensorFlow's inbuilt API, the data is already pre-processed. Okay, so by loading tf.load, okay, I'm saying within so there are three arguments that I'm passing. One is the dataset that I'm passing. The dataset is IMDb reviews subverts 8K, so that is the name of the dataset. Okay, then the second argument I am passing is with info. So the point of with info is, as I've said, the dataset is already pre-processed, but I need that pre-processing information so that I can see how the pre-processing has been done. So to get that information for any dataset about the pre-processing, we say with info is equal to true. And thirdly, the third argument is as supervised. So in the as supervised argument is also true, because of course we need supervised data for training any classification network. So this is a classification.
So that's
Okay.
what will be the
So
information in data set?
yeah.
No, I'm asking what is a data set? I mean, what will be the information in data set? Can you explain?
Yeah, I'll explain. I will come to that. That's what I've said. We are going to use it in the code.
Okay.
Yeah, we are going to use it in the code. So if I just broadly explain, see, dataset contains my dataset. That is my training data and testing data. And by data, I mean my training examples and my training labels, and my testing examples and my testing labels. But you see, we are working on text data, but we cannot input text to the network directly, because in computers everything goes in the form of numbers. So we need to convert this text into some form of numerical data. So that conversion has already been done by TensorFlow. But how that conversion has been done, that information is in the, we are loading as an info. Now we are going to see what kind of information, what kind of translation from text data to numerical data has been done. So we will see the properties using info. Okay, actually, I might
No,
not
I'm
be able to
for
read the.
example, can you show how what is the input data of movie set? Like, is it name, actors' names, and review, or like what is the input set from the IMDb? What we are receiving here?
Okay,
Like, how does
yeah, I
the
will show
input
that.
data looks?
Below, I will show that. Yeah,
Okay.
okay. Below, I will show that.
Should be there in the IMDb website, right? This is all the data
No,
should be
this is
present.
IMDb reviews data set. I mean,
Okay.
you can search about this. It's actually really extensive data set. It's not in IMDb website per se, but this is a data set that's been, I don't know exactly who generated this data set, but yes, I will just um, show some of the examples in the IMDb data set. Okay, I actually, yeah, okay. So, sort of the thing I said that is data set is actually in the form of uh, is a text data, right? So text data needs to be encoded into numerical data. So for encoding that numerical data inside the info, okay. So inside the info there is an encoder already coded. So encoder is the functionality that has been used to encode my text data to numerical data. So from the info we are going to attain this functionality and actually see that what kind of encoding has been done. Now the very first property of any of the text data is the vocabulary. By vocabulary I mean how many unique words are there in this text data. So when I'm talking about IMDb reviews data set, my vocabulary is sizes 8185. Okay, so index. Okay, yeah. So basically, the IMDb dataset had a vocabulary size of 8185. So here by vocabulary, what I mean is that number of unique words that were present in that dataset. So there were 8185 unique words present in the dataset. Okay. Now I'm going to show you how the encoding has been done. So let's say if I'm giving a text string, how the text string will be encoded into numerical formats for this dataset. So I'm going to do the encoding for some text like hello TensorFlow. So let's say I have a text hello TensorFlow. Okay. So I want to encode this hello TensorFlow in the numerical way that can be inputted into my network. And so I'm creating a sample string by the name of hello TensorFlow. So this is a string that I'm creating in the name of sample string, and the string contains the string hello space TensorFlow full stop. Okay. Now what I'm doing is from the encoder, I'm calling encode. Now this encode will take a string and convert it into the numerical values. So what it will do is it will take every word in that string and convert that every word into one numerical value. So numerical value. Okay. So I'm going to print it. So when the input string was hello TensorFlow and I encoded that string hello TensorFlow into encoded string, string, the values that I got was, so it converted this string into a set of numerical values. So the string hello TensorFlow got converted into these numerical values, 1, 2, 3, 4, 5, 6, 7, 7 numerical values. Okay. Now the question arises how this conversion has actually been done. Okay. So how a string called hello TensorFlow, which has two words, one space and one full stop, got converted into these 7 values. So there's one very peculiar property about this encoding is that, let me show you. So what it did was it encoded the parts of the sentence. It broken down the string into small chunks and gave integer value to each of the chunk. Okay. So what it did was it broke down hello TensorFlow into these chunks. The first chunk is hell. The second chunk was O space. The third was 10 answer and FLO and full stop. And to each of these chunks, it gave an integer value. And how these chunks were decided. So what they did was they took all of the training data, okay, and any word in the training data is that chunk. So any word in the training data. So what they did, they took all the unique words in the training data and assigned one integer value to each of the unique word. Now, but the issue of this assignment is, so let's say a word that was assigned in this, let's say I can create another string. So sample string 2 is equal to, because I know some properties and just helpful stuff. So this is another string, okay. And if I print and if I just create its encoding 2, okay, and if I run it now, so you can say, so see for hell what it did was it converted the hell into 4025, 7975, where the 4025 was hell 7975 for dot. So what it means is, so the word hell was actually inside the dictionary. So in the initial data, in the training data that we had, the word hell was in the dictionary, but the word hello was never in the dictionary. Okay, so what it did was it broke down the word hello into two parts. The part that it understood hell and the next part that it didn't understood O space. So it broke down the word hello into two parts so that it can understand at least one of the parts, hell and O space. And similarly, it broke down the word TensorFlow into multiple parts. Those parts can actually understand. So because hello TensorFlow, these two words were not in the original dictionary, it broke down these two words, hello TensorFlow, into small chunks which were actually inside its dictionary. Uh, So this is how the breaking has been done. Okay. And wait, this is some. Okay, so we want to see some of the examples of this data set, right? And let me just show you one of the examples of this data set. Okay. Okay. So this is the info that how the decoding has been done. So this was about the decoding. So decoding has been done by creating a dictionary. That dictionary maps each of the unique words present in my dataset to a specific integer. When I run any given string through the encoding of that dictionary, I can get the encoding for that word. Actually, the IMDb. Okay, wait. Dataset. So let's. I can show you some of the examples of IMDb review dataset. Mm. Sentiment analysis. So that is the data source. Okay, it's actually a big file, 129 MB. Uh, okay, so it will actually the internet is not that good there. I would have to download a data set and it's big, so I won't be doing that right now. Okay, so but what this data set has, so this data set at an input has a review, a sentence. Sentence in the form of review. That the review, the input is this movie is good, and corresponding to that input, this that string, we have a label that is whether this review is a positive review or a negative review. So corresponding to each of the strings inside the data set, the string can be this movie is good, or the this is a thriller movie with a good suspense. So for and each of the strings, like here I show the string hello TensorFlow. So for each of the string there is a label whether the movie review is good or the movie review is bad. So the sentiment of the review is what has been encoded in this dataset. So it's a binary classification dataset in which the input to the network is a text, that is a string, and the output is a binary label specifying whether it's a positive string or a negative string. And the encoding of the string has been done by this encoding function, which encodes each of the words in the training data to a specific integer values. So, and since this encoding has already been done, it's actually I cannot actually show the original data set here because the encoding has already been done. For that, I would have to download the raw data set to show you, which will actually take time, and internet is not that good here. And if I try to download it, my Zoom connectivity will suffer. So, but yeah, you can actually see the dataset is in Kaggle. You can actually go to this dataset later on. It's in Kaggle IMDb review dataset, and you can actually see exactly what's inside this dataset. But yes, it's a text data in which the input is in a text format and the output is a binary classification output, whether the input text has a positive sentiment or a negative sentiment. Okay.
But the input CSV file has 5 columns. Right? Can you go back to that? We don't need to see the data, but we can see the column
Yeah.
names. It has a type, review, label, and file, right? So
Yeah. Type, review, label, and file. Yes. Okay, so type is the first thing is whether it's a train data or a test. So the any row, so a row is a data. Okay, so whether it's a train or test data. Review is the actual data, the actual text data in that row. The like this movie is good. So that's the review, and it's not showing all the labels.
is the label is the movie name maybe? Is it,
No. The
question
label is the sentiment. Label is
okay.
the sentiment actually. Okay, so label.
Question is like,
So there are two sentiments.
so question is like, is this
Yeah.
data for one movie or it's a mix of multiple movies? The review data, like,
It's a mix of multiple movies.
okay,
Yeah, it's a mix of multiple movies. So there are like 98,000 values in that. So
okay,
there are
okay.
98,000 samples in that taken from IMDb, reviews from IMDb. So there are it's a data of multiple movies. You can actually see some of
Okay.
the data. Okay, so it's data of multiple movies. Okay,
So mainly we are taking that
so
string
that
of the
was
review,
about
right? Review string, and we are converting to our encoding. We
yeah.
are encoding it.
Encoding. So that's been so that information, how that conversion is going on, it's an info. Now in the data set, now I'll explain what is inside the data set. Okay, so inside this data set, so if I actually say print data set, okay. So what is this? See, when I'm printing this data set, okay, so when I'm doing tfds.load, so when I load any dataset through the TensorFlow's dataset API, the dataset is actually loaded in the format of a dataset adapter. So it's an inbuilt class of TensorFlow in which you can actually build your own data sets. So dataset adapter is a class of handling data. Okay. So let me just show you a bit more about that. So if you go to TensorFlow, TensorFlow. Tutorials. So inside this tutorials, yeah. So inside this tutorials, customize, bigness, yeah, load data. So that's okay. Picture. I want a tutorial for TF data. ML basics, load and pre-process data. This one ML basics. This one customization, distributed training. Exactly this one. Yeah, that's tf.data. Yeah, tf.data, building TensorFlow input pipelines. So tf.data is actually input or is a, so now to handle the data for training deep models, TensorFlow has come up with its own API called tf.data. So instead of using, so previously we have seen we can store data in the form of lists and numpy, right? But we can rather than using list and numpy, we can actually use tf.data. So tf.data stores the data set not in the form of numpy or a Python list, but it actually stores the data set in the tensor format. So, and I have explained before, by tensor I mean that anything that can be executed inside the GPU, that's a tensor. So by storing the data in directly in the tensor format enables really fast processing of the data and really fast networks, because so if I load the data in the NumPy format, data is loaded inside the RAM. And whenever I'm running a code on the GPU, so there's a big so there's a big bottleneck when the between the communication of RAM and the GPU, that creates my bottleneck. So if I actually use tf.data instead of NumPy to encode my data set, so what it will happen, the data will already be in a tensor format, which will already be in a ready to import version of the GPU. Yes, the state of the data might be in RAM, but the data will be in a tensor format so that it can directly be imported to the GPU, and the bottleneck of the communication between RAM and GPU is highly decreased if I'm using tf.data instead of NumPy data formats. And I might not be able to go into much details of tf.data because it's again a really itself it's a really big concept, but you can see that tf.data, you can search tf.data TensorFlow and it will give you a guide of it, and through that guide you can exactly go through how this tf.data is used. Okay, so tf.data has one of the class is dataset. So this dataset class actually provides many functionalities about the data. Okay, so we are going to see a couple of functionalities here for the class. So now I have shown you dataset. So So you can see that this is a dataset v1 adapter. That is, it is the class dataset of the tf.data. So whenever there's an object of the class tf.data, its type is a dataset or dataset v1 adapter. Basically, dataset v1 adapter is a hybrid class, so that the same dataset class can be used in both TensorFlow 1 and TensorFlow 2, but we can easily create a tf.data class itself. But the properties of dataset v1 adapter are same as the properties of tf.data.dataset class. So whatever the properties of dataset class which is shown here, the same properties are there in the dataset v1 adapter. So I can, so even if it's saying it's a dataset v1 adapter, I can easily say that this dataset is in the format TensorFlow's dataset class. So inside the dataset, there are two things: train data and testing data. Okay. So what I've done, I have taken the train data from the dataset and made train examples, and I've taken the testing data of the dataset and made test examples. Okay. So now let me print my train data. So train examples. Yeah. Okay. So you can see my train examples is again a dataset class, and it has the shape of this is the shape of the data, and the type is integer. So it's my integer data in which the shape none. So by shape none, what I mean is that um, it's a class of the data of variable shape, and the shape actually doesn't make sense right now, but you can actually see here that my training examples are a TensorFlow dataset class in which each dataset is a TensorFlow integer value. Okay. Now, so these are the proper. So why we are going to use a dataset class? Because we can actually create efficient training pipelines. So whenever we are creating a training pipeline, like in last session, we used fit to train. Okay, so we use model.fit to train my network. So inside that model.fit, what we did was we gave our training data and we gave our training labels. So while giving the training data and training labels, I gave those training data in the NumPy format. And from that NumPy format, I told my the fit command actually took the data inside the batches and print. But here we won't be giving in the NumPy format. The whole data is in the train examples. My train examples is all the complete data in the format of TensorFlow tensor. We will be creating data generator format. Okay. So by creating a data generator, what I mean is I will creating a command and I will give some properties to that command. So if I input that command inside my fit, so that data generator will automatically take my data from train examples based on the command that I'm creating. Okay, so I will create a uh, command for this object train examples. Now this is an object of my class dataset, the TensorFlow's dataset class. Train examples is an object of that class in which my complete training data is there. So for this, I will be actually creating a command so that I can input in fit, and based on that command, the data will automatically go inside my network so that my network can be optimized. Okay. So now the properties of the command is, so I'm going to create a load. So this command can also be called as a loader. So I'm going to create a data loader. So to creating the data loader, I'm creating a train dataset loader. So I'm creating a loader in the name of train dataset. Okay. So this loader will be applied over my training examples that had my training data. Okay. Now what it will do is it will first shuffle my examples. Okay. And it will shuffle by some buffer size. uh, okay, so basically when we shuffle a dataset, the shuffling is taken the shuffling happens in out place. So let's say I have an array and I want to shuffle that array. I would have to create another array which I can use to shuffle my previous array. So whenever I have to create another array to do any processing, that processing is called an outplace processing. So So shuffling is an outplace in which I have to create additional space so that I can actually perform that operation. But many times what happens is our input array is very big and we cannot afford to create another array of the same size as our input array. So what it does is we actually give a buffer size as to what's the maximum size of that extra array that will be used while doing that outplace operation. So since shuffle is an outplace operation, we can actually give a buffer size that you won't be using an outplace array to perform the shuffle of more than the size of buffer size. So so for the first task is you have to shuffle my train examples, okay, but the outplace array that you use should not be of the more size as the buffer size, okay. Now secondly, I have to create a batch of it, right? So from all the data set I have to create a batch. So I had the whole data. So let's say my data had 60,000 examples, okay. So my data had, let's say, 1,000 examples, right? So 1,000 examples and 1,000 labels. So first what I did was I shuffled the data and I again got 1,000 examples and 1,000 labels, right? Now I need to convert this data set into batches. So let's say I want to convert this data sets into multiple batches in which each batch size is 10. So what I need to do is I need to convert the data set into 100 batches, okay, where each batch size is 10 comma 10. So I need to convert this data set into 100 batches where each batch size has 10 examples and 10 labels. So for that the function that I use is batch function, okay, but here I have used another function known as paired batch. Now this paired batch is very peculiar when it comes to sequence processing. So whenever there's a sequence processing we need paired batch, because see what examples is, let me take one sentence. So this is a good movie, okay. So this movie is bad. So whenever we have an image data, one of the very good properties of an image data is that each image is of the same size, or it's very easy to make every image of the same size. But when it comes to text data, every sentence that we are having will be of different sizes, right? So here you can see the first sentence has 5 words, while the second sentence has only 4 words. So all these 1,000 examples, all the 1,000 training examples that we're having, each of the examples were having a variable size, okay. So now problem is, even after shuffling, each of the examples have variable size. But the issue comes, so when I'm creating batches, so if I'm creating a batch of 10, now again inside the batch of 10 each example will be of variable size. And I need, but when I'm giving an input to the network, the input shape has to be fixed. So it has to be a consistent input shape that I need to give to my network, okay. So what I will do is I will calculate the sentence which has the maximum size. So in this case, the sentence which had the maximum size is the first one. It has 5 examples, and I will pad
That's
all the sentences with, yeah.
whatever last 2-3 minutes you explained, right? Batch size, buffer size versus batch size. Can you explain one more time? Sorry.
Oh, okay. Okay. So buffer size is for shuffling. So what I need to do is I always need to shuffle my data, because shuffling the data is always good while training the network. Okay. So I always need to shuffle the data. But the problem with shuffling is the shuffling is an outplace operation. That is, let's say I have a array of size 1,000, and if I need to shuffle this array randomly, I need to create another array of size 1,000 so that I can shuffle this array. So it's an outplace operation. But sometimes my array is really big and I cannot afford to create another array of the same size. So let's say my array is already of the size 10,000 and I have a limited memory, so I cannot create another array of 10,000. So in that case, I can specify that the second array that will be created, which will be used for shuffling my original data, I can specify the maximum size of that array. So that is called buffer size. So in this case, I specified my buffer size as 10,000. So that means the second array I will be creating will be of the size 10,000 only. It won't be of the size greater than 10,000. And even if I am shuffling, let's say 100,000 examples, it will, the outplace array that it will generate for shuffling, it will only generate of the size 10,000. So buffer size is always given whenever we have a memory limitation, so that for because shuffling creates a lot of takes a lot of memory, because it creates a new uh, array array. So if you want to decrease the size of the new array or restrict the size of the new array, because we have limited memory, we can use the buffer size inside the shuffle. That the new array that will be created, that will be of uh, 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 that won't be of more than 10,000 elements.
So for example, like you mentioned, if total data set size is 100,000, so
Yeah.
by shuffling it, we are only taking 10,000 off out of 100,000 data points.
No, we are not taking 10,000. So what it's doing is, for shuffling, what it's doing is, it's first taking the first 10,000 values of that array. So I have an array of 100,000 values. Okay. So better example. Okay. So let's say I have an array of 10 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is my array of 10 values, and I want to shuffle it with a buffer size of 2. So what that will do is, I will first take 2 elements, okay, and then shuffle these 2 elements, and then I will take first 2 elements, and then I put it in the outplace array, and then shuffle these 2 elements and put them in a random order in the original array. So then again I will take the next 2 elements, my 3 and 4, and then I will shuffle them somehow, and by shuffling 3 or 4, maybe again 3 or 4. Okay. But ideal
Got it.
ways I take all of those and shuffle them, but here I will
Got it.
shuffle by chunk.
Got it. So instead
Uh,
of taking the entire size to save the RAM and this one, we are doing by buffer sizes. Okay. Got it. Thank you.
we're doing the buffer size. Yeah. So that was about buffer size. So because whenever we train, whenever we start an epoch, we always shuffle our data. So before starting any epoch, we always shuffle the data. So that's something that's always done. So okay. Now once the data is shuffled, I need to extract the data in batches. So let's say my data set had 1,000 values. Okay. So my data set had 1,000 values. Now I cannot give input all the 1,000 values directly to my network. But my network can only take, say, 10 values at a time. So I need to convert my 1,000 values into batches of 10 values. Okay. So if I take my 1,000 values and convert them into batches of 10 values, so I will have 100 such batches. So here my batch size is 10. So I'm specifying at what batch size you need to now split the data. So while making a padded batch, the first thing that I pass is my batch size. That is, what will be the batch size, or what will be the size of the data that will go inside the network at one particular time. So let's say I had 1,000 original examples, but at a time I only want my network to see 10 examples. So my batch size will be 10, and 100 such batches will be created. So what my system will do, it will create 100 batches of batch size 10. So it will, let's say I've given an array of 1,000. I'm reshaping that array in the format of 100 into 10. So I'm splitting my array 1,000 into 100 chunks. Each chunk has 10 values. Okay, and where each value is a sentence. Each of the value is my movie sentence. There's
So
a problem with movie sentence. So
does it needs to be equal batch sizes, or it will in the last 2-3 batches it will, is it okay to have, like, for example, if there are 10,000, does the batch size needs to be exactly divided by each batch needs to be same number, or
yeah, I understood the question. Okay, so let us say my batch size was, so in this case, for 1,000, let us say I gave the batches of 6. Now 1,000 is not divisible by 6. So my number of batches won't be a proper number. It will be like it won't be a proper number. So if I'm using the data class, what it will do is so in the last batch it will have a less number of elements. So it will automatically make a batches such that all the batches will have 6 elements, but the last batch will have 3 or 4 leftover elements. So all the leftover elements after creating of the batches, and that will be in the last. So last batch will be small depending upon how many elements are left. So it will automatically
Got
take care of that. We can
Thank you.
specify any batch size. Yes. So, but the problem with, so now that was the batch size. But in the batch size, what there is, so in that batch, I have said that so let's say my batch size was 10. So in that batch, I'm saying I had 10 items. So what is that item? What is that one data value that I'm having? In this case, that data is a sentence. Now the problem in sentences are of variable lengths. And I cannot give variable length input to my network. I need to convert all of these sentences to a fixed length. So what it will do is, so inside a batch, okay, so I have a batch of 10 sentences. I will find out which is my lengthiest sentence. So let us say my lengthiest sentence was, this is a good movie. So this sentence had 5 words. So I will convert each other sentences to 5 words. I will pad each of the other sentences so that my each of the sentence has 5 words, where pad is also a word. So the previous sentence had 4 words. This movie is bad, so I padded one here. Okay. Now let's say I have another sentence, good movie. Let's say. So here I am going to pad 3 times, so that again the size becomes 5. So now what's happening is all of the sentences in the batch have a size of 5, have 5 words in them. So I'm going to pad all of my sentences of a particular batch to the maximum size. Okay. So uh, for that, I'm going to use padded batch method. So that padded batch method breaks my data set into batch size and pads each of the batch size to the maximum size. And to specify, the padding has to be done for the maximum size. So this is what we specify, where the first column is none and the second column is empty. Okay. So what we mean by none and empty, that now my data, the shape of the data will be none. The first element is none because it's dependent upon the batch size. And as I've told, we can have variable batch sizes. The last batch can have small number of elements. Okay. So that's why my first axis is none, because my first axis of the data is none. So if I'm specifying any values in my second axis, what I'm saying is to, so if I'm not specifying any value in the second axis, my system will automatically take the maximum padding value and pad accordingly. So if I'm not specifying any value in my second axis, that is my size of each of the item. So second axis is the size of each of the item. It will automatically pad each of the item in a batch to the maximum length it is. So whenever I use this train dataset pipeline to extract the data, it will automatically do all of these operations on the my training data and return me a batch. So what this train dataset will do is, so first it will take all the training examples, it will shuffle them, and then it will return me one padded batch, just one padded batch. And then next time it will return me the second padded batch. And then next time it will return me a third padded batch. And then next time it will return me a fourth padded batch, and so on. Till the time it has returned me all of the batches. So once it has returned me all of the batches, it will again shuffle my data and then again keep on returning all of the padded batches one by one on the new shuffle data. So all of this thing will it will automatically keep on doing on my training data. I need not to code them. I need not to specify them. And since the training example is already in the format of TensorFlow data format, every of these operations will be really fast because they will be applied on a tensor. So So shuffling the data and padding the data and then creating batches of the data, everything now will be done by TensorFlow itself. You don't have to code anything, and it will be really efficient because we are using TensorFlow dataset API here. So this train dataset is like a training pipeline. So it doesn't have data, but it's a command. You can say it's sort of a command. So whenever I call this command, it will apply these operations on my training data. So training data. So hope this thing is clear. What is train dataset actually? Okay. So similarly, I'm creating a command for extracting test data. So for the test data, I'm using test examples, and for the test examples, so you can see for test examples, I have not applied any shuffle because I don't need to shuffle test data. I need to shuffle training data, but there's no need of shuffling test data. So I'm not applying shuffle. I'm just applying padded batch so that the test data will give me padded batch. Okay. One change in TensorFlow 2.2 is if you are going to use TensorFlow 2.2 and forward, you don't need to specify these kinds of shape when you're using padded batch. So in padded batch, you can only give batch size, and if you have not specified what kind of padded shape that you're using, it will automatically pad each of the dataset to the highest shape. So this is in TensorFlow 2.2 because padding to the highest shape is actually a default thing that everybody uses. So if you don't specify your own padding, it will automatically do padded to the highest shape. You don't need to specify it. But in all of the previous TensorFlow versions, you have to specify the using giving a shape that what kind of padding needs to be done. Okay. Yeah. So now, okay. So now what's happening is, so now what has happened? So let's say my batch. So okay. So my batch size was 64, right? So what I specified my batch size was 64. Now my data has been converted into the format of, let's say my original data had some examples. Okay, so it got converted into 100 examples, where each exam 100 batches, where each batch size is 64, and each element has a maximum of 100 words. Okay, so this is now my data set. So my data set is, I have 100 batches. Each batch has 64 elements, that is my batch size, and 100 is the maximum length of every sentence that I'm having. So I have, so basically by padding, I have created every sentence into 100 length sentence. So every sentence has now 100 words in it. Okay, and each word is actually represented by an integer. So I have 100 values representing a sentence. So this is my complete data set. So the dimensionality of the data set is 100, 64, 100. So it's a three-dimensional array of the size 100, 64. Okay, where this 100 is one sentence.
Your voice is broken. That's, can you repeat one more time? I think because internet connectivity, we are not able to.
Yes, my hostel, there's been internet issue today.
Sure.
Okay,
Yeah.
so,
Can you please repeat that? What you said about this 100?
Yeah. So now, so let's say So in my original data set, I had 6,400 sentences. Okay. So in my original data set, I had 6,400 sentences, and each of the sentence were of variable length. So each sentence was having variable length, which was, let's say, the minimum length was 1 and the maximum length was 100. Okay. So what I did was I have padded each of the sentence to the maximum length, right? So now my data set is become, I have 6,400 sentences, and each sentence is having 100 words, and each word is represented by an integer, right? So my data set is in the shape of 6,400, 100. So that is, I'm having 6400 sentences, and each sentence is having 100 integers in it. So this is my data set right now. Now I have broken down this data set into a batch size of 64. So what I mean, I've broken down this data set into batch size of 64 is, now I have 100 batches. Each batch has a size of 64 elements. So I have 100 batches. So inside each batch, I have 64 elements, and the size of each of the element is 100. So this 100 is my sequence length. So that is how large is a sentence. So that's called the sequence length. So how large a sentence is. So that's a sequence length. So 100 is the sequence length that I'm having. That is how large my sentence is. That my sentence is having 100 words. So that's my sequence. Okay. And each word is a single integer. And in a batch, I'm having 64 such sentences. And overall, I'm having 100 such batches. So at one particular time, the input to my network that will go is 64, 100. So this will be the input to my network. So network will take 64 batches, and each batch has a sequence length of 100. That is 100 integers. Right. So this thing is clear to everyone till now here.
Yes.
Okay. Yeah. So, but there's an issue. See, whenever we are whenever we encode anything in the form of integers, there is one very big issue whenever we encode anything in the form of integers. The problem is, so because integers have some relationship between them. So let's say what I've done is I had a word cat, and I gave integer 1 to cat. Okay. Then I had word dog and gave integer 2 to dog. And then I have another word aeroplane and gave integer 3 to the aeroplane. So if I'm encoding my sentences in integer format, there's one very big issue. The issue is that that I'm encoding a hidden relationship between them. So what I'm saying to network is that cat plus dog is equal to aeroplane. So that is something I'm saying to my network, because my network understands numerical relationships very well. It's based on numerical data. It's based on numerical expressions. It understands relationship between numerical data very well. So if I am encoding each of the word into an integer, the problem with that integer is that I'm here saying cat plus dog is equal to aeroplane. Another problem is that I'm saying that there's a big difference between cat and aeroplane than cat and dog. But I mean that maybe yeah, that's the case, but that not might be the case in every encoding. So I need to remove. I cannot use the integer encoding as it is. Despite I have used the integer encoding, I actually cannot use the integer encoding as it is. Okay. So what I need to do is I need to convert each of this into 100 encoded encoding. So we all know what 100 encoding is. We've used for classification task, right? So now I need to convert this 100 into 100 encoding. That is, for cat, what I will say is cat is 100, dog is 010, and aeroplane is 001. Okay, so now rather than having integer values for each of the word, I'm going to have 100 encoding values for each of the words. So because by using 100 encoded values, each of these vectors, each of the three vectors are, because orthogonal to each other, sorry, orthonormal in this case, orthonormal to each other, the distance between each of the vectors is constant, that is 1. And you can even see that the Hamming distance between each of the two vectors is fixed too. So if I take any two vectors, the Hamming distance is 2. So the distance between each of the words is fixed. So so now what I'm saying is each word is unidistant from all of the other words. So there's no hidden relationship between these words. So it's always good to encode them in a 100 encoded format rather than integer format. But what will be the problem is, okay, let me go above. My vocabulary size was 800 8,185. That is, I have 8,185 unique words. So what the issue would come if I convert this data into 100 encoded format? My each input now will become 64, 100, 8,185. So I have 64 sentences. Each sentence has 100 words, but now each word, rather being an integer, is now a vector of disparate dimension. Because now each word is a one-hot encoded vector. Each word is, rather than being an integer, is now a vector of 8,000 dimensions. So just for easiness, let me write 8,000. So each word is a vector of 8,000 dimensions. So now the input to my network that's becoming is 64, 100, 1000. Okay, so this is the input to my network, right? But the problem with this input, yeah. So for any recurrent network, if I create any recurrent network, whether it be RNN, whether it be LSTM, whether it be GRU, the input to the network is always in the format of this. That is my batch size, comma my sequence length, and my feature dimension. Here my feature dimension is 8,000 because each word is represented by a vector of 8,000 values. Okay. So this is my batch size. I will repeat. So this is the standard thing. So batch size, sequence length, and feature dimension. So this is a standard way in which my data will actually go inside any LSTM. Okay, my data will inside go any LSTM. But again, there's an issue. So this 8,000 dimension is very large. If I create a network in which my input is 8,000 dimensional input, and if I create any LSTM over this, the LSTM will have a huge number of parameters, and that system is definitely going to overfit. So what I need to do is I need to decrease the dimensionality of each of the vectors. So I need to decrease this dimensionality. So somehow what I need to do is I need to convert it into format of 64, 100, let's say small dimension of 64. Okay. So my first layer of the network would be that. So this is the input to the network. Okay. So my first layer of network would be that takes the 100 encoded vectors and converts them into an embedding of 64. So it will be a fully connected layer or a dense layer that will take this 8,000 as input, which will has 8,000 neurons in input and will have 64 neurons in output. So which converts each of the feature dimension from the size of 8,000 to 64. Okay, so this is going to be my very first layer of the network. So you understand the task that the first layer needs to do. So the first layer will get an input of the size 64, 100. So the first layer where 100 are my integers. So each word is represented as an integer. So my first layer needs to convert integers into 100 encoded format and then learn a fully connected layer so that these 100 encoded formats get converted to a lower feature dimension. So that is my first layer's task. So that layer is called embedding. So that layer is called embedding. So what this embedding layer will do is it's a inbuilt layer in layers, not layers. What this embedding layer will do, it will take a data in this format, that is batch size, sequence length. Okay, and then it will convert the data into first one-hot encoding, that is batch size, sequence length, feature dimension of one-hot encoding, and then make a fully connected layer so as to decrease the feature length to some other value of 64. So while making this layer, there are two things that we pass. The first thing that we pass is what is the vocabulary, what is the size of one hot encoding that it will create. So that I am passing as my vocabulary size, that is my 8,000. So 8,000 is my first argument to this layer embedding, because what's the first task of this layer? The first task of this layer is to convert into one hot encoding vectors. Now for converting into one hot encoding vectors, it needs to know that what is the total number of words. So what is the dimensionality of the one hot encoded vector? So first argument that we pass the dimensionality of the one hot encoded vector, that is 8,000. And the second argument which we pass, what is the lower feature dimensionality that is required. So that is 64. So what is so by defining this embedding layer with a vocab size of 8000 and a feature dimension of 64, it will take a data of 64 into 100, convert it into one hot encoding 100, 8000, and then learn a fully connected layer to convert this one hot encoding into lower feature embedding. So now what it had done is it had learned an embedding for each of the word. So this 64 dimensional is an embedding for each of the word, a unique embedding for each of the word. So this layer is going to learn a 64 dimensional embedding for each of the word in my input sequence. So now after embedding layer, this is the output that I will get. That is 64, 100, 64. Where 64 is my batch size, 100 is sequence length, and 64 is my embedding dimension. Okay. So is the embedding layer clear? Okay, this is
Yes.
actually important. Why we are doing this? This is actually really important. Okay.
But how did you come up with that line number 64? Like, I mean,
See, how do we come up with the number 64? Okay. The problem is, see, the lower this number, the less information we are having about a word. Okay, so the lower this number, the less power to the network. The performance will be lower. But if we increase this number a lot, so this is the input to my LSTM. So if I increase this number a lot, the parameters in my LSTM will drastically increase, and that might create overfitting. So again, it's a hyperparameter we need to come up with. So a lower number will create problems of underfitting, and higher number will create problems of overfitting. So again, we need to keep on experimenting with this number to find out for our problem what is the optimal number, optimal embedding size that we want. So this is because just a toy example, hence we have come up with 64. But in my experiences, what I have seen is embedding size. I have trained a few things on text data. So I have seen an embedding size of 256 or 512 works well. Because the embedding size of 256 or 512 have enough information but does not cause overfitting. But if I make my embedding size is 1024, a really large embedding size, that causes overfitting, and an embedding size of 128 or lower, that causes underfitting. That is, that embedding size is not enough to represent my data. So again, it's a hyperparameterization. We have to keep on changing these to see for our problem what is the best hyperparameter that we want. But since this is a toy example, so we are actually taking a very small hyperparameter so that it gets trained very easily.
but how do we know whether when you mean to verify whether it's overfitting high like that, like based on what we know that okay, 64 is very small, let's increase it to 128, or so based on what output do we determine that value?
Hello?
Sorry. So based on what, like once it is done, like once this operation is done, how do we determine like this is low or this is high? So we need to change the parameter, right? Like for example, if I do 128, after running
Yeah.
something, then how do I know that, okay, I think I need to change this value more? So how do, based on what?
Based on what? Okay. So that's based on my training loss and testing loss. Okay. So so for given any network, okay. So if we are given any network, we first train the network on our training data, right? So when we are training the network on the training data, the training loss will keep on decreasing epoch by epoch, and even testing loss will keep on decreasing epoch by epoch. So we keep on seeing the relationship between training loss and testing loss. Okay, so what would happen is we fix one parameter of 64. So initially we have fixed 64. We will see how the training loss and testing loss is decreasing. So if the 64 is very small, it's underfitting. What would happen is that after one particular point, the training loss will stop decreasing, and even testing loss will stop decreasing. So at that point, what we can say is, since the training losses stop decreasing, my network has stopped learning. So that means my network needs more information to learn. That means my network needs more parameters to learn. The number of parameters inside my network are less, it's not able to learn. So if my training loss and testing loss while running multiple epochs after one point stop decreasing, I can say my network is underfit. That is, I need to increase my parameters inside the network. So now I will keep on increasing my parameters. But what might happen is, after, let's say I've increased this parameter to a large value of 512. So at that time, what might happen is that when I'm training my network, as the epochs are going, my training loss will keep on decreasing. But let's say my network was running for 100 epochs. Okay, so for all the 100 epochs, my training loss kept on decreasing. But what what testing loss did was, testing loss decreased for first 50 epochs, but after 50 epochs, the testing loss started increasing. So at that situation, when testing loss started increasing after 50 epochs and training loss started decreasing, that's overfitting. That is, my network is trying to cramp up my training data, but not generalizing. My network has very huge number of parameters that is trying to cramp up my training data. That the loss on my training data is completely decreasing, but network is not able to learn the underlying pattern inside that problem. And because it's not able to learn the underlying pattern, my testing loss starts on increasing. So that is a situation of overfitting. So we need to analyze how for epoch to epoch, how the training loss and testing loss are changing. So for ideal way, what the ideal case should be, that training loss should keep on decreasing, but testing loss should decrease to a specific value. After that becomes sort of like stagnant, not neither decrease nor increase. So in that kind of situation, my system is neither underfit nor overfit.
Got it. Thank you. Thank you. Thank you.
Actually, I have an example right now for it. Wait, let me show it. Yeah. So in this example, you can see the okay. I'm. It's not allowing me to share any other screen. It's only allowing me to share Google Chrome screen. Why is that? Wait, let me start sharing again. Let me reset my sharing. It's not allowing me to share any other screen.
You stop
Sure,
this
sir.
sharing, then again share. Yeah.
Okay, so I want to share the screen. So this is actually a real-time training that I was doing today of one of my networks. So you can see the network is run for 139 epochs, and my training, this is my training loss. The training loss is almost of the order of, you can see, around 1. So sometimes 0.9, sometimes 1.01, sometimes 0.9. So my training loss is approximate in the order of 1. Whereas my testing loss, you can see, this is my testing loss. My testing loss is really high, 1.6. So there's a big gap between my testing loss 1.6 and my training loss. So what is happening now? My system is overfit. So the problem is training loss is now is keep on going low, but my best testing loss was 1.5 and my current testing loss is 1.6. So after approximately 100 epochs, what happened was, at 100th epoch, I achieved training and testing loss of 1.5, but after 100 epochs, my training loss kept on decreasing from 1.5 to 1, but my testing loss increased from 1.5 to 1.6. So this is classic overfitting, and my training loss is decreasing while my testing loss is increasing. So this is my classic situation. You can easily see the accuracy as well. The accuracy is 68, where here the accuracy is sometimes even being 76 and more. So this is classic overfitting that we are seeing here. So that's why once I saw this overfitting, I stopped the code. So once I saw this overfitting, I stopped the code using a keyboard interrupt, because I saw this network is overfitting. I need to decrease the number of parameters inside this network. So I just did it before this session. So that's why so this I could show to you. So this is classic overfitting. So now I changed my network this time. So now I'm experimenting and I've changed the total. So initially my number of parameters was 15 millions. Now I've decreased my network so that number of parameters become 12 million. Now I will train this network again in 12 million parameters to see how it's performing. And now I will keep on decreasing my number of parameters until my network stops overfitting and I get a good performance. So this is how we specify these numbers. So this is one of the just real-time examples that I'm working on these days right now. Okay, wait. I should choose full. Okay, now it will allow me to share each screen. Yeah, now it's sharing my Google Chrome, right? My collab.
Yes.
Yeah. Okay, so now I find out how to share each and every screen. Okay. So this is how we actually choose the number 64. Okay. So now by choosing this number 64, after the embedding layer, the size becomes 64, 100, 64. Okay. So where this is my sequence length and this is my feature dimension. Right. So now after this, I'm making an LSTM layer. Did sir cover bidirectional LSTMs? Did sir cover bidirectional LSTMs? Bidirectional.
I don't remember.
Okay, so maybe not so by okay, what a good image. This is a good image. Internet. Why can't okay. Okay. So when we talk okay about LSTM, what we talk is we talk that LSTM is a sequential model. So what it will take is it will take the first input inside and then compute the hidden state. Then it will take the next input and compute the hidden state, and then it will take the next input and so on. So it will go from first input to the last input. So that's my traditional LSTM. So what bidirectional LSTM does is it first goes from first input to last input, and once it has computed the final state here, so on that final state, it then goes from last input to first input again. So it goes in the both directions, first in the forward direction and then in the backward direction. So that's my bidirectional LSTM. So rather than a single LSTM going from first input to the last input, now my bidirectional LSTM will go from first input to last input and then from last input to the very first input. So that's my bidirectional LSTM. So that's just a simple change that it will go forward as well as backward, but all of the internal workings of LSTM is same, but only this is the change. So here we are going to use bidirectional LSTM. So in this code we are using bidirectional LSTM. So to use any RNN in bidirectional format, we'll first call the layer bidirectional. Okay, we'll first call the layer bidirectional, and so and inside this layer, so you can see, so this bidirectional, so inside this bidirectional, I'm calling which RNN layer it needs to bidirect. So first I'm calling a bidirectional layer of the keras. By calling bidirectional layer, I'm saying I'm going to create a bidirectional RNN. But what type of RNN? I'm then specifying what type of RNN, that is an LSTM. So now, so what I'm saying is after my embedding layer, I'm creating a bidirectional LSTM. And in that LSTM, I'm specifying a number 64. So what this number means is, so if I'm specifying number 64, what it means is that the dimensionality of the hidden state. So LSTM had that C vector, right? or A vector. Some people call it A vector or C vector. Some must have covered it. So that C vector, so dimensionality of that C vector. So we specify the dimensionality of that C vector. So we know the dimensionality of the input is 64 dimension. We specify the dimensionality of the C vector as 64. 64. Okay. So now I'm creating an LSTM which will take such an input, okay, and which is having a C vector of 64 dimensional. So what it's doing is, so it's taking this input. So x1, x2, x3 to xt. So it's taking this input, and each input is 64 dimensional. So the number of x1, x2, x3 to x100. So this is 100. There is number of x in my sequence, that's 100. So this is the 100 that we specified here. That is my sequence length. So here, this can be seen as this is my first, second, third, and this is my 100. Okay. And this 64 is the feature dimension of each word. That is, each of this x, it's a 64 dimensional vector. So this x is a 64 dimensional vector. This x is a 64 dimensional vector. This x and this x is a 64 dimensional vector. So inside the LSTM, I'm giving 164 dimensional vectors at a time, and LSTM will see them in the form of a sequence. And after seeing them in the form of sequence, it will return to me again 100 vectors of 64 dimensional. That is my dimensionality of C, the C vector. So whatever I specify the C vector, it will return to me that dimensional 100 values. Okay. So this LSTM should return to me. So batches will remain the same. So for each of the sequence, it will give me a 64 dimensional value. So is this thing clear?
Yes.
Yeah. Okay. Okay. Oh, in this code, one thing is missing. You might have to add it. False. First, let me show it too. Okay. All right. So, so this LSTM is going to give me 64, 100, 64. Okay. But there's one argument inside the LSTM that's called return sequences. Okay. What I mean by return sequences is whether the output that is returning, it should be in a sequence format or not. That is, should it return each of the sequences? So at the input, I had 100 sequences. Now I'm saying, should it return all the 100 sequences, or it should only return the last output? So LSTM can do that, right? LSTM can take as a sequence as the input, but only return me last output, or it can return me all of the internal sequences. So if I'm having return sequences as true, it will return me all of the sequences. So it will return me a 64 dimensional output for all of the 100 sequences. But if I make it false, so if I make return sequences false, what it will do is it won't return me all the previous 99 sequences. So all of these bytes from 1 to 99, it won't return me at all. It will only return me the final byte. Okay, so it will see all of the whole input sequence and then only return me the final output. So if I do return sequences is equal to false. So if I put return sequences is equal to false, the output of my LSTM won't be 6464, but it will be 64164. So this will be my output of my LSTM. That is, it's going to return me only the last output and not all the previous 199 outputs. It's going to return me only the last output of the LSTM. So in this case, I'm doing return sequences is equal to false. And by default, LSTM has return sequences is equal to false. So if you're using an LSTM layer and you're not specifying any type of return sequences, by default the return sequences is false. So by default, if I'm just using an LSTM layer, it will only return me 64 1 64 rather than returning me the sequence length of 100. So it will just return me the final output at the final sequence. That's it. Okay. But actually it will return me in the, so that was just the one. I can remove that one. So it will return me 64,64. That is, it is just returning me the final output. And that's in the format of batch size, comma, my feature dimension. So finally on this 64, I apply a dense layer of, let's say again 64. So I get 64,64. And since it's a binary classification, in the last layer, I need a single neuron. And so for binary classification, I apply a dense layer with one neuron. So this is my complete network, which takes my input as 6400. That is a sequence of 100 words. It converts each word into 100 encoding. It converts 100 encoding of each word to an embedding. So now it has 100 words in which each word is 64 embedding. Then the LSDEM understands all of these 100 words and then provide me a final output. And over the final output, I apply FC layers to get my one output, which is a binary classification of saying whether the input sequence, that is the input 100 words, corresponding to a positive review or a negative review.
Can you repeat that, what you repeated from 19 to 24, like one more time?
Yeah, okay, so this is the summary of what we have done till now. So my input was of the format of, I had 64 sentences. Each sentences had 100 words. Okay, and initially each word was encoded in an integer format. So I had 64, 100. So I had 64 sentences in a batch, and each sentence was 100 words, and each word was an integer. So first, what I did was, first this network converted these integers to 100 encodings. So since my vocabulary size was 8,000, so they converted each of my integer to a 8,000 vector 100 encoded 8,000 vector. So now my data has become 100, 8,000. Now my first trainable layer, the embedding layer, what it did was it learned a mapping, it learned a fully connected layer between the 8,000 and 64. 64, effectively converting each of the word to a 64 dimensional vector. So now in each sentence, I had 100 words and each word was a 64 dimensional vector. Now LSTM saw all of these 100 words and finally gave me an output of 64 dimension. So that is, if I go to this value, so I had 100 words and each 100 word is having 64 dimensions. So LSTM saw all of these 100 words and then finally gave me a final output of 64 dimension. So here that is the final output of 64 dimension. And over this, I applied a fully connected network to finally get me a single value, which will give the probability whether the input sentence had a positive review or a negative.
So the final output, when you say 64, 1, so each sentence now it's classified into false or true.
Yeah, it's sentence classified into good or bad. Yeah, positive review or negative review. Yes.
Positive or negative. For all 64 sentences, we are classifying it now, right?
Yeah, we're classifying. So this this one value will give the probability of the review being positive. So if this probability is high, the review is positive. If this probability is low, if this value is low, the review is negative.
Correct. So each review, like that 64 represents each review, right? So so each review we are classifying into positive or negative based on the number. Okay.
Yes, exactly. So now, wait. So now I have since done the model, we can see the summary of that model. So since I have shown you all of the above, let's see it in summary as well. Okay. Okay. So the model summary is so the embedding layer, that was the first layer. The output shape of that layer is none, 64. Now the first none represents my batch size. The second then represents sequence length, because again, I can input variable sequence lengths as well. One batch can have a maximum sequence length of 100, other batch can have the maximum sequence length of 5, the next batch can have a maximum sequence length of 10, and so on. So that's why we are not specifying any sequence length. I just took an example of 100 in this case, but we cannot specify, by default we have never specified a sequence length. So the sequence length is none. And even we can always change the batches as well. So while making the network, the batches is also none. So it's none, that is decimal batch size, comma sequence length, comma feature dimension. So embedding layer output is batch size, comma sequence length, comma feature dimension. Then my bidirectional LSTM layer output is batch size, comma 128. Okay. Oh yeah, it will be 128 in this case. Sorry. Oh yes, I did made this mistake. Okay. So when I was talking about LSTM, what I said was that the LSTM will take all of the 100 inputs and give me 164 dimensional output, right? But that will be for forward pass. Since it's a bidirectional LSTM, it will then again see all the inputs in the backward way. So that is, it will first see the 100 input, then 99, then 98, and so on. And then it will return me the very first output. So you can see in the forward pass, after seeing all the inputs from 0 to 100, it returned me one output. But in the backward pass, after seeing all the inputs from 100 to 1, then it will return me the forward output. Since there are two outputs coming of 64 dimension, it will combine them into a 128 dimension. LSTM was bidirectional, the output dimension is 128. But if I remove the bidirectional, so if I remove the bidirectional, so now the output of the LSTM is 64. Because now the LSTM is only a forward pass LSTM, it's only giving the final output. But if when I was having the bidirectional LSTM, I was having both the outputs of the forward pass as well as the backward pass. So for the bidirectional LSTM, my feature dimension was 128. So here, rather than 64, it's 128. Because of the layer had none 64, and after that my LSTM had none 128. Now this is my feature dimension. Then the first dense layer batch size 64, and the final dense layer batch size 1. So this is what I have shown previously, and this we can even see that this in the model summary as well. So this is my network, which is having an LSTM, which takes an input as sentences, and to each sentence it classifies whether it's positive review or negative review. Finally, I will compile this model using binary cross entropy loss and Atom optimizer and provide accuracy as metric. And then while training the model, since I have created now while training the model, I don't need to specify any NumPy arrays. Since I had created a command for extracting my training data, my train data set command, we created a command for extracting my training data. So in that fit, I will actually just give that command. So now you have to fit that model using this data command. So I've created a model. Now you need to fit this using train dataset. Where the train dataset was a command that we created dot shuffle and dot parrot batch. So we created a command train dataset. So inside the fit, I will give the train dataset that is the command to reprocess my data, and then number of epochs. Then I will provide a validation data. Validation data is a test data in which after every epoch, it needs to give me its accuracy. Okay, validation steps, I'm not actually clear. You will see what validation steps is. You can actually see in the documentation. I've never used validation steps, but they had it in this code. But I don't exactly know what validation steps does. But it does not hinder the training process at all. It's just something to do with validation, nothing with training. But I'm not pretty much sure what validation stuff does. But now, since I've created an LSTM model, I can fit it using the train dataset command I did and specify the epochs and my validation data in which I give my test dataset. So this model.fit will finally train my model, and then I can evaluate the model on my testing data. So that will give me its performance on the testing data. Okay. So any doubts in that?
No, that's yeah. We'll go through the video one more time and we'll try to do it in Colab and see. Yep.
Okay. So let's not do the second code today. I mean, it's
Yeah,
because
already it's at
it's on.
2.5 hours. Yeah.
Yeah, exactly. So next week we will go through the second code. I will tell sir that I was only able to cover a single code.
Yes.
So
Please update
let's
him
keep
what all we have covered.
yeah. So let's keep it till here only today, and we will cover in the next session. Text generation we will cover in the next session.
Sure. Thank you so much, Daksh.
Yeah, you're welcome.
Thank you, that's bye.
Bye.